My name's Chris Colahan, and I work on the indexing team. And I just wanted to actually quickly introduce our distinguished visitor today. Today we have with us Michael Isard, and he's brought along with us in the front row here a large contingent of the Dryad team from Microsoft. And so he's going to be talking about the Dryad distributed computation system, which is Microsoft's superset, you could argue, of MapReduce. It's a more flexible version of MapReduce, and he'll tell you all about it, and it's very interesting research. And I believe they also use it for real production systems. Michael is a distinguished researcher from Microsoft. He's worked for DEC and Compaq in the past, and I guess I'll just let him take it from here. Also, a quick reminder from the AV folks. This talk is being video conferenced to other sites, and they can't hear you asking questions. So if you have questions at the end, please go up to the microphone. Also, this talk is being recorded to be put externally on YouTube after the talk. So if you want to talk about your ultra-secret confidential projects and share them with Microsoft, please do so away from the microphone after the talk. Thank you.
Thanks a lot. So yes, I'm going to talk about the Dryad project, which is research mostly done a year or two ago with these co-authors, some of whom are here. Mihai and Ioana are here. You can talk to them afterwards. So I've given a bunch of Dryad talks now, almost certainly none to an audience this specialized. So I'm going to skip very quickly over the motivation of why anybody might care about distributed execution, but I just want to get a couple of basic ground rules out of the way. The idea of the project was to make a general purpose execution environment for distributed data parallel applications. And overall in the design, I mean, you have to make design trade-offs when you're building a system. And we chose to concentrate on throughput of the whole cluster rather than latency of any particular job, particularly if there are failures. You can wait for timeouts and stuff. This isn't for real-time response. And we're ignoring a lot of security issues and stuff by assuming you have a private data center with single administrative domain, all that kind of stuff. And of course, the goal is that the programmer just writes the program, runs it as though on a fault-tolerant single computer, and the system should be in charge of doing all the distributing the data and the resources and scheduling and all that good stuff that you're used to. So I'm going to describe in some detail the computational model of programs that Dryad supports, but just to give you some idea of where the thing that I'm going to be describing fits in the stack. I'm going to argue lots of programs and lots of programming models can be represented as the kind of graph that Dryad understands. And Dryad is really at the middleware layer of the thing that will run those for you. So Dryad itself doesn't know anything about the semantics of the program or the programming model. So in that sense, it's more general than MapReduce. We don't have those specific operations built into it. And so it's an abstraction layer between the programming model on the top that now just has to manipulate graphs, and Dryad below that just takes any old graph that it's given and executes it. And the advantage of that we thought was that you could have a nice simple regular scheduler that doesn't know anything about semantics, just knows about graphs. And that's where you build in all of the stuff to do the fault tolerance and the scheduling policy and stuff. And then that becomes independent of which particular semantics of the programming model you have on top of it. So as I said, this is kind of middleware. So you can write programs directly on top of Dryad, and people do. And you should think about the people that do that as needing to be able to write good sequential C++ code. It's useful to do that if you want a lot of generality and if you really want to tune it for particular performance. And you can also do interesting things, which I'll talk about a bit later, customizing, for example, the dynamic optimizations that you want to put in there. So there's a lot of flexibility writing directly to the Dryad layer. But almost everybody that uses the system is actually writing to some higher level programming model that's layered on top of it. And I'm going to say very little about those things. This talk is really about that middleware layer, not about the typical user experience of the high level programming. And so before I get on to any technical details, I just want to have a couple of slides about how this came to be. So the Dryad project started out as a pure research project. I'd just come off working with the search team on the V1 of the MSN Search that launched in the beginning of 2005. So I was definitely motivated by some of the experience I had at Search and some of their applications, but also by just the general research question of how to make it easier for programmers to express parallel and distributed programs. And also, my background is actually in computer vision, and computer vision machine learning are fields that can consume a lot of cycles, but where the developers are typically not systems programmers and maybe don't exploit as many cycles as they could. So that was another motivation. So there was an obvious technology transfer path for this to Search, and Search do use it, but remember that Microsoft has got a lot of other things beyond Search, and so Dryad is designed to support some of that as well. So it's used as a research platform inside MSR for things like scheduling, distributed database execution, that kind of thing. And also there's a bunch of people who just have a few machines lying around. They want to do some data processing that doesn't really fit into SQL Server or whatever, and they can just fire them up and run Dryad programs on them. And so some of the flexibility is paying off there, that we're not just using it on giant clusters for big search applications. And then I just want to do a bit of a plug for MSR, and because I think it was a good place to be able to do this research. The projects just start up bottom up. So essentially, this project started because I thought it would be fun, and I was able to con some of my colleagues into agreeing that. But then we have the collaboration across the company that means that we can actually get other people using it and leverage their research. And the fact that we have a flat structure, particularly in the lab at Mountain View, meant that I can have all these diverse interests in learning and also systems and get to work on them all. And then, of course, I get to come and give you the talk because it's open too. All right, so I'm going to talk very briefly about the runtime and how the cluster's set up. And then I'll go for most of the talk into what kind of programs Dryad can run, and then I'll give a couple of case studies to sort of illustrate that. So this is probably a pretty familiar picture. This is the cluster that Dryad assumes. So when a Dryad program runs, there's a single centralized coordinating process, which we call the job manager, that holds the graph in its mind and makes all of the scheduling decisions. And that's some libraries that get linked in with the user application that constructs the graph. And then on the cluster, there are just a few services that this needs to get bootstrapped. There's a name server so it can find out what the cluster resources are. And then every machine in the cluster has a daemon that will fork processes on its behalf. And they can talk to distributed file systems and the network and all the usual stuff. And then Dryad also supplies some libraries at the Vertex executable, which communicate through this fabric back with the job manager so it can get updates on what's going on. So, pretty much what you'd expect. So a Dryad job, the restriction on a Dryad job is that it has to be representable as a directed acyclic graph. And as you can see, it's a multi-graph. You can have multiple edges between vertices. So the graph, each of the circles is a program that processes some number of inputs and generates some number of outputs. The edges are channels which are sending data items along them. And then there are some virtual vertices which are inputs, for example, in the distributed file system and outputs in the distributed file system. And the channels can be of various types. So a channel can be persisted to a temporary file where this just writes it out to the disk and this guy's going to read it in later. Or we have TCP pipes and also shared memory channels within a process, which I'll talk a bit about in a bit. So as I said, the inputs and outputs are just virtual vertices in the graph, so that keeps the whole structure regular. And this is extensible, so we can support different types of file system. And when you have a distributed file system with a partitioned file, then obviously a single named object there can expand into a whole bunch of virtual vertices so that you can do reading in parallel. And similarly, at the output, a bunch of them can write out to individual vertices, which at the end get coalesced into a single file at the end. So the channel abstraction we made the choice to make this a sequence of structured items, which are C++ objects. And the point of that was that so we could get this implementation flexibility. So for the temporary file and TCP pipe channels, there's serialization code that gets called and puts this into buffers. But when you're doing it down shared memory, the pointers to these can get passed directly. So you can have a whole bunch of vertices in the same process connected by these shared memory pipes and have very low overhead because they're just passing pointers around. You don't have to worry about serialization overhead there. And in keeping with the idea that this is middleware that should be flexible, we basically have no restrictions on this data model. The application designer can just derive anything from the base type and put any data in there that they want. So then the main design question is why a directed acyclic graph instead of something else? So we came to the conclusion that this is the natural, most general design point, and I'll go in for a couple of slides about why I think that. But basically, if you add cycles, it gets too hard, and it's probably a mistake to be simpler. And so, I mean, the reason for that is partly DAGs support the full relational algebra, and you can do other things as well. I mean, in particular, it's nice to be able to have multiple inputs of different types coming into a vertex and multiple outputs of different types coming out of the vertex. That gets used a lot, obviously, for example, for joins on the input, but also if you're taking in some data type and splitting it out into two completely separate streams for other processing, it's nice to be able to do that naturally at the vertex instead of having to work around it, which is, I guess, I mean, you can always work around this kind of thing. But also, for sort of from software engineering, there was the idea of this layered design I was talking about at the beginning, where we didn't want to bake any semantics into the scheduler, so we could keep it nice and simple and just have it deal with graphs. So going in a bit more detail, some of the reasons why you want a general DAG and not just put the semantics of particular stages in there. So one is that if you go and look at a lot of applications, they look, I mean, a lot of them look a bit like SQL queries, that they look like these very uniform stages happening one at a time. But of course, in practice, once you've done some dynamic optimizations, the actual things that get executed in the data that flows gets a lot more irregular. So you could be doing some kind of merge tree so that these are on the same machine and these are in the same switch. And maybe some of them don't generate any output, so you just wire them into some virtual vertex that throws it away, and you don't actually bother sending the data and discovering that this is empty. And also, of course, there are lots of non-trees that are useful. So this is an example of distributing into equal size ranges. For example, if you want to do a sort of some key that you don't know the distribution of, you start out with your randomly partitioned inputs. You can just tap off some small sample of that data, compute some histograms, send it back here and repartition it, and you end up with this thing that's not a tree. And when you combine that with the fact that now this thing that looks regular isn't really regular because you're doing all those merge optimizations, you've really ended up with a general graph anyway. So your scheduler is probably going to need to handle that, so you might as well just put it in as a first-class part of the scheduler. Why do you not want to add cycles? Well, I mean, I guess you guys are probably familiar with this, but two reasons mainly. Scheduling is easy because you can just run a vertex anywhere once all of its inputs are ready, and because it's a DAG, there's a topological sort of the graph, which means you can always get from the beginning to the end. Assuming, of course, that the channels are finite length, which is something that we assume that our programmers will respect. So, once all the inputs arrive, the thing could start running. Then once it finishes running, it can mark its output as ready. This is the picture for the files. Obviously, if you have pipes or shared memory, the channel is marked as ready as soon as the producer starts running. And then the other thing that it makes much simpler than an alternative is fault tolerance, especially if you assume that the vertices are deterministic, or at least that the programmer is willing to put up with anything weird that happens to the extent that they're not deterministic. Because, of course, if a vertex is running and it fails, then you just run it again and nobody knows the difference. And if one of its inputs disappears, you just traverse up the graph and rerun that. And it's also, as you are no doubt familiar, if one of these guys is running slow, you can just run other copies elsewhere. And because everything's deterministic and there are no cycles, by induction, you can see that the output's going to be the same from all of them. So you can just use the output interchangeably from whoever finishes first and not have to worry about a lot of bookkeeping. So the final sort of part of the design space is that we wanted to make sure that the graph was going to be modifiable at runtime. And I'll give a bit more detail about the actual mechanisms we use for that. But basically, the application passes a graph in and says run. And then as the graph executes, the application can register objects that get callbacks at various interesting times. And when it sees those callbacks, it can decide to modify the graph. And so you can do a lot of optimizations that way. And you can basically modify anything downstream that hasn't run yet, is the way to look at it. So once a vertex is executed, you can't delete it, and you can't change the number of inputs or outputs that it has. But before it's executed, you can do whatever you want. Question?
When you say you can do this, you mean the person who has created the graph and submitted it. You're not talking about the scheduler doing optimizations by modifying the graph.
Right, so the question is, who does the modifications? Does the scheduler do it, or does the application do it? So in terms of the abstraction layer, the scheduler doesn't do the modifications. The scheduler calls back into the application. Of course, there are some very common dynamic optimizers which sort of come with the libraries that you can plug in. But in terms of the abstraction layer, they're above the level of the... They're extensions to Dryad. They're not part of the scheduler. That's interesting. Okay, so another way that we think about organizing these graphs is a lot of times, many programs, you get a bunch of vertices which are essentially all the same, that are just partitions of some larger logical operation. And so we have a concept called stages that allows you to group these together. And so the way that works is that there are these stage manager objects. Each vertex in the graph has a single stage manager as its parent, and by convention, a stage manager is going to be managing a bunch of vertices which are essentially of the same type, although that's just a convention. You can actually do anything you want there. And so the stage managers are useful for reporting, because you get all the statistics about the running of the thing aggregated by stage manager. But it's also the sort of locus for where these the callbacks come in on the events as the vertices are running and as they complete and fail. And so the stage managers are in charge of gathering specific statistics for a particular type of vertex in the graph, and so that you know, if you're trying to do estimates of how long something is supposed to take, you know, that stage manager sees all of the pairs, and so that's the natural place to build the model of the running statistics. And also, that's where you put the algorithm to decide when to start running when to tell the scheduler to start running duplicates, that kind of thing. And so again, as in the previous question, these in the design, these are all extensions, but there are standard default stage managers that basically most people use that do the obvious statistics collection and duplicate execution algorithm. And then one other layer beyond that is that, so now you can lift above the real graph. There's this stage manager graph, which is implicit. And between two pairs of stages, you can have one of these dynamic connection managers, and that's how the dynamic optimizations happen. So you can put a link of these between any pair of stages, and then that gets callbacks when there are interesting events, basically in the upstream stage, when vertices in the upstream stage finish, or when vertices get added or removed from the upstream stage. And this is where most of the dynamic modifications happen. So you know, if you're doing some kind of merge tree, it'll get a callback every time some vertex finishes. You know what the size of its output was, where it ran, and then that lets you build merge trees that are optimized for data locality and that kind of thing. And also, because you're getting callbacks when vertices complete and when they're added to a stage, you can get these pipeline stages where you originally pass in just a single strand of a pipeline, but every time the upstream, the guy at the bottom of the pipeline gets a new vertex added by some dynamic optimizer, that just ripples up, and so you end up with the whole pipeline being filled in. And so finally, I just want to go back again to the point about the channel abstraction and what actually happens in the vertices. So when you're writing a vertex for a Dryad program, you're writing this program that has some abstract channels coming in and some abstract channels coming out. But inside the process that's actually running, of course, there may be some whole graph of these where they're wired together using these shared memory FIFOs. And this subgraph is itself just a vertex program that accepts a serialization of what graph is supposed to be built here. So it's all just layered on top of the basic APIs. There's no specific support needed to do things like subgraphs. So now I'll just go into a couple of case studies of actual applications, and I'll start with a small application and then a larger one. And this will pull out some of the differences that we found between using small private clusters and large shared clusters. So the first example is this database query. So this comes from the Sky Server database, which was something that Jim Gray worked with astronomers on. And it's a published set of database queries about astronomical objects. And this was the longest running one on SQL Server. And it's basically doing a three-way join on some tables to find a gravitational lens effect. And I'm afraid I can't tell you more than that about what that means or how this finds it. But essentially, you're starting off with two tables. One has a whole bunch of stars in. And for our purposes, each row in the table is just an ID of a star and its color. And then you've got a neighbor table which just says these two stars are close to each other physically. And so that just takes two star IDs and says that they're close together. And the task is to find neighboring stars that also have similar colors. And so the way they chose to do this was by a three-way join. So first of all, you just join the color table with the neighbor table to find, and you output this temp table, which has the color of the original star and the ID of the neighbor. And then you just join that temp table with the original table a second time and to pick up all the ones that match. Then now you've got the star's ID and its neighbor's ID. So essentially the plan that SQL generated looks a lot like this. And for this task, this was done a while ago before we had any SQL-like front end. So we just manually coded this up in Dryad. And we manually partitioned these tables by range so that the same range of primary keys lives in each of these partitions. So what's going on here is we start out with these partition tables, partitioned by object ID. And then the first stage is just doing the first join. So you're just pulling out the color and the neighbor ID. And then the bulk of the work happens here, which is really just repartitioning this temporary table in order to make it ready to do the second join. So coming out of here, we had these things which were in some random order because we were keyed on the neighbor ID, and now we want to just repartition it so it'll be keyed on the object ID and we can do the final join. So we do that by first doing a distribute into hash buckets. Then we take the merge of all of these inputs. So each of these hash buckets gets inputs from all these. It does a non-deterministic merge, and then it does an in-memory sort. And then finally you can do the second join, because now these are all sorted and partitioned correctly. Again, you can just do another streaming merge join and get the answer out the back. So what I want to talk about a little bit here is how we actually optimize this. So you can just write this in Dryad, and each of these arrows can be a temporary file, and it'll write them all to disk, and it'll take a while. But the first thing you can see that you can do is you can pull these two together, all of these pairs of things together into the same process, because there's no reason to have this data escape. So you just replace that by a shared memory FIFO instead of a file. And then similarly up here, we're going to pull 4 of these merge sorters and 4 of these in-memory sorts into the same process, and also put them in the same process as second join. And the reason that we chose 4 here is because the machines that we were running it on happen to have 4 CPUs. So this way, we get the in-memory sorts to be all parallelized. And so this is sort of a typical thing. You know, we didn't have to write a parallel sort because we could just put more partitions in and put 1 on each CPU. Obviously, this was done by hand, but you know, that's the idea. But then an interesting thing happened. So the key here is that these are all in-memory sorts, and so you have to design the partitioning such that you won't exhaust the memory of the machine by this much data. And as I said at the beginning, we did a manual partitioning, so we just picked the right number there so that we wouldn't exhaust the memory of the machine. But if you happen to know that the entire data set all at once fits in memory, then you can actually replace all of these additional edges by TCP pipes, because you can afford to hold the whole working set in memory of the whole across the cluster all at once. And you don't have to ever persist this to disk, because you know, the important thing is that all of these processes can be in memory, and then you get to put all of these in the same process, because now you can put these as FIFOs, put these as TCP pipes, and run the whole thing at once. And that's where you start to get even better performance. So this is just the performance graph. This is the original SQL Server, which is obviously doing a lot more than we're doing, but just for comparison, that we don't have really terrible performance. And this is the scaling graph where we were doing the 2-pass sort. So that's this one where we were persisting the output of this distribute onto the disk. And so what this graph shows is we did a partitioning into 40 partitions, and we just ran the same program on between 1 and 9 machines. So we had a 9-machine cluster, and we get a pretty linear speed up, as you'd expect. And we haven't tried that on much huger things, but you know, that's what you want. But here, when you, at 6 machines, now the working set will fit in memory of the aggregate across all the machines. And now you can go from 6 to 9. And now you're getting this linear speed up at least for 4 data points. But basically, it doubles just by eliminating that extra write out to disk. And you know, the important thing to notice there is that we didn't actually change the code of any of that was running in any of the vertices. All we're doing is manipulating the graph at the graph level in order to do those optimizations. So now I'll move on to a larger scale example. So this is a fairly standard query histogram computation. So you start off with some log file that's been partitioned into n partitions. It's going to extract queries from those logs. So the queries are going to be much shorter than the entire log entry. Repartitioned by the hash of the query into k buckets, and then compute a histogram in each bucket. So I'm not showing you a full sort of histogram out the back. We're going to end up with each of the k buckets having a histogram computed. So the first way that we thought of doing this was this topology. So this is sort of the gross structure of it. The queues are going to read in the log files and distribute them. The Rs are going to reduce them, basically. And within each of these queues, we actually have a bunch of more primitive vertices connected together by these shared memory channels. So the first guy just parses out these log lines and throws away everything except the query. The next guy does the hash distribute. And then we do a little in-memory sort of each of those, do a partial reduction while we're here, because you might as well now that they're sorted. And then when you get to the R, you do a merge sort, because these were all, the outputs of these had already been output in sorted order. So you can just do a merge sort here, then do the final reduction. And you know, we thought this seemed like a reasonable topology for doing this problem. But it turns out that this was quite inefficient for a couple of reasons. One is that the actual partitions that were stored on the disk are much smaller than the memory of the machines that we were using. So essentially, the queues didn't have enough data. There's some overhead in running each vertex. So that was a waste to have n be so large. And then it turns out to be inconvenient to get one of these guys to read from so many inputs. So if n is 100,000, having this guy read 100,000 inputs puts some strain on the infrastructure, which wasn't necessary. So this is what we eventually ended up with. And it looks a bit weird as a topology, but I will show you in a minute what actually happens. But this is the basic topology that the application hands in at the beginning of running the job. So now we changed Q prime to start off with a non-deterministic merge, so you can have more than one input coming into it. Then it does the parsing as before, and then it does its in-memory sort and then the partial reduction. But notice it didn't do any distribution here. And then it writes that out to this T, which is doing a merge sort of its inputs, even though there's only one input here, you'll see in a moment. Then it does another partial reduction. Then it does the distribute. And then the R is as before. So we've split the queue into two stages, and we've allowed each queue to take multiple inputs. So then when it actually runs, we put dynamic optimizers on there. So as I said, the application hands this in to start with, but the first thing that the dynamic connection manager on this set of edges does is to group these by the location, the machines that they're running on, and modify the graph to expand this out so that each queue has up to some amount of data coming into it. So you specify some maximum amount of data that you want to have because you're doing an in-memory sort there. And then this dynamic optimizer just does the grouping for you. And so then as these start running and as they generate outputs, we have another dynamic optimizer here that's looking at the size and location of the outputs that are being generated. And when you get enough of these, it splits off a new T from here, modifies the graph again, and starts running that. And so eventually, once all of these have completed, each of them gets their own T. Then once all of these outputs are ready, you can start running the final reduce. And so the statistics that this actually ended up doing on some particular run was we started out with 100,000 partitions, about 10 terabytes. And the original grouping per machine got this down to about 10,000 queues, so it was using about a gigabyte per queue. But then, as I said, there's a big data reduction when you pull out these queries from the logs. So the output of this is now very small. And so we only end up having a couple of hundred of the T's being generated. And now, when they do their distribution, these guys only are reading a couple of hundred inputs instead of tens of thousands of inputs or hundreds of thousands of inputs down here. And so the statistics of what it ended up being at the time that we ran it on the particular cluster. So in both cases, I want to pull out what was going on here when we were optimizing these. In both cases, we didn't change any of the code that actually ran inside one of those vertex circles. What we were doing was graph manipulations. We were rearranging the computations, pushing them up and down the graph, and we were changing the type of the channels. And what you should be thinking here is that this kind of graph refinement is much easier for a system to understand automatically than looking into the code that you wrote inside that circle and trying to do parallelization there. So we've tried to split out, get the user to supply the sort of atomic bits of code in these circles, and then let the system have at it on these graphs to try and do the best it can using some rearrangement rules. And of course, once you start bolting on higher level front ends, the user doesn't actually have to see any of this stuff. The user just writes something, for example, that looks a bit like a SQL query, and then you can build something that looks a bit like a SQL query planner that does all of that work, both statically to come up with an original good one, and then dynamically to try and refine it once you know where the data actually lives and how big it is. So I'll say a little bit about what we've found when we've been doing this on the difference between small and large clusters. So we have a bunch of people that are using very small clusters, tens of machines, and there's essentially no failures when you hardly have any machines, and you know exactly what the resources are, and you know if you buy a new machine. So the incentive for the people that use it that way is they want to get as much performance as they can, because they're trying to solve some specific problem as fast as they can. And so things like the pipes, as I showed in the Sky Server database example, become really useful, because you're really, that extra write to disk could double the speed, as you saw. And you're willing to spend a little bit of time on the particular program that you wrote to work out how much RAM it's using, how much CPU it's using, maybe try and shoehorn as much onto each box as you can, knowing the number of processors as in the Sky Server database example. And so you use a bunch of features in Dryad in order to do that. But then when you go to these large public clusters where you have to assume that the resources are completely unknown, because the person that manages the cluster might just take half of them away or whatever, and there's always some unknown number of failures, etc. You really end up trying to go for best effort across the population of jobs, sacrificing the particular performance for any particular job, and then you don't end up using some of these more sophisticated features, because it's just too hard to predict exactly what's going to happen. You'd rather have the isolation. You'd rather just say, I'm going to devote this machine to this process because I don't know what that process is going to do, and it's better not to mix them up. So the fact that we have this generality in Dryad makes it suitable for both of these worlds. But if we were really only ever dealing with this, then we wouldn't necessarily be using all of the features that we have. So finally, I'll just say a little bit about the higher level programming models that we have on top of this that most people are actually using. So there's something called SSIS, which is built into the SQL Server product. It used to be called DTS. I don't know if any of there are SQL Server experts here. But essentially, this is something that the product already ships with, which lets you draw a graph a little bit like a Dryad graph and put arrows between boxes and put SQL queries in the boxes. And it all runs on a single SQL Server instance. So a team in Ad Center at Microsoft that were already using these, they just wrote themselves a Dryad application that takes one of these workflows on a single SQL Server box and splits it up, and then uses Dryad to run the split up partition thing. I don't have any pictures to show you, but that's kind of nice, because you have the whole SQL Server tool chain for all the debugging and everything, and then at the end you just press go and this thing goes and runs it on their cluster. And they've been using that for some of their ad billing pipelines for over a year now. Then there's a sort of quite simplified front end that got put on by some people in the search team, which essentially looks a bit like Perl with a few SQL-like operators. And this has extremely low barrier to entry, and it's sort of like a turbo Unix pipes distributed. And it's very easy to use, and people use it for all sorts of things, but it doesn't have amazing performance. And then Yuan, who's in the front row here, for a while has been leading development on Dryad Link, which I'll say a little bit more about. So I don't know how many of you are familiar with Link, but you can go read all about it here. It's coming out in Visual Studio 2008, but you've been able to download it and use it since last summer, I think. And it's a way to integrate SQL-like queries into C# and Visual Basic, and maybe some other .NET languages. And you end up with programs that look a bit like this. So this is now a C# program, but it's building an expression tree that looks a bit like SQL. You've got select clauses and group bys and order bys. But each of the things that lives in here is just any old C# function that you wrote, or is using whatever .NET libraries you want. And this turns out to be a really nice way of expressing parallel and distributed programmers. You've got this generalized relational queries, so you can put in any any application operators you want. You don't have to just use the SQL ones, and you can use any structured data type that you want. You don't have to just use the base types from SQL. But what the developer sees when they write it is essentially this sequential imperative program that's doing whatever they want, and then building one of these query trees. And the way that LINQ is designed, it does lazy evaluation so that by the time the user actually tries to retrieve any of these, the system gets to see the whole expression tree, and then it can go off and do whatever it wants with that expression tree. And in particular, you can go and run it on the cluster. And so this is nice because simple SQL-like queries continue to look extremely simple and are very accessible and approachable. And you can hide all the details of, sort of vertical specific stuff in libraries, so that, you end up writing this, your less technical developer doesn't have to understand any of the details. They just get to write something that looks like a SQL query. It's all using these C# objects, but they're hidden off in a library somewhere. But the hope is that it makes big programs a lot more manageable than any of these more toy scripting languages. You can use all of the libraries that you already have, and you have a real type system under there. And so we have programs of thousands of lines. We don't have hundreds of thousands of lines yet, but you really start to see the advantage of a type system over, for example, something in Perl when you start to have large. We ported programs and certainly found bugs where the untyped nature of Perl was masking some bug. And it's all built into the tool chain for debugging, which is nice, so we don't have to write new tools for a new language. And so this is a great front end for writing moderately complicated programs on top of Dryad. And I guess I'm finishing kind of early. Not as many questions as I had prepared for, I guess. But in summary, as I said, we have this general purpose platform which is designed as middleware for distributed data processing. And as I said a few times, it's very flexible. And for our use, that has been quite important because it's used in lots of places on small clusters for research, etc. But it does actually scale up properly to larger clusters with thousands of machines and very large data sets. And because we have this flexibility, people have been able to experiment with different programming models and have found different things are suitable for different needs. So that's it. Questions? Yeah. Okay.
Could you go back to the slide where you discussed the speed up when using in-memory sorting?
When this one?
Okay, this one. Yes. So I'm wondering the following. So you motivated the development of Dryad by high throughput computing rather than low latency. Could you discuss to the extent to which disk was the bottleneck here? For example, did you measure the number of seeks per megabytes read? I was wondering.
This is all sequential access, so we didn't measure the number of seeks anywhere. I mean, SQL Server is obviously not necessarily doing that, but by the time we'd done the manual partitioning, we set up this problem so that everything was just sequential.
I see. So in this specific example, data was not read of buffer cache.
Correct. So this is basically running at disk speed. I mean, we have, I guess we had 4 disks on each of those machines, and I think we just had them striped. I think it's in the paper. I can't remember. It was a while ago. I think that's just 4 disks striped into a single volume. And so, as I recall, the first stage is purely I/O bound. This stage obviously has got 2 parts. First of all, it has to read it in, and then it has to sort it, and that's serialized. So the different phases are bound by that, and then the amount of output is trivial. So there's no it's like 5,000 bytes come out at the end.
Yeah. Hi. Could you compare this product to IBM's stream processing core?
No, I'm afraid I can't really.
Okay. Thanks.
What name should I use to look it up?
I think it's IBM SPC. They had a Sigma
SPC.
paper last summer on it.
Okay.
Yeah.
I was wondering if you could say something about the ability to recover from failure and the fault tolerance ability of this system. Particularly with respect to large clusters. You mentioned that it is a big issue with large clusters where machines fail, etc.
So, I mean, I just put the simple slide up there, right? We're assuming everything's deterministic, and we're assuming that there are immutable inputs and finite length channels. So, by induction, the data on each channel is deterministic. And so it really is, more or less as simple as this, that the vertices, remember, are linked with libraries that let them communicate back to the job manager. So the job manager can distinguish between the failure case where the vertex itself failed and where one of the inputs had a read error. And so basically, if it got a read error, it goes recursively back and tries to regenerate the input. And if it got a failure, it just runs it again.
Which could mean that you have to basically replay everything from the original source, unless you have some persistency along the line.
Yes.
You also have a single job manager, right?
That's right.
Which is a single point of failure, I assume.
Correct. And so the job manager is running a deterministic state machine, so you can log out what the job manager is doing, and you can do suspend and resume that way. But we haven't done I mean, it's a state machine, right? You could do it as a replicated state machine if you wanted to, but that didn't seem worth doing for the number of, proportionally, the failure is much less likely on the job manager, and you can always restart the job from scratch.
Yeah, and I assume you could also use some persistency on the job manager.
Right, you can log and do suspend resume, that's right. I mean, that's because we're not too focused on the latency, it's easier to do that than to keep a reliable state machine going.
What fraction of your users end up using Dryad link as opposed to manually coding the graph and the application?
Almost all of the users use some high-level front end. Very few people are writing it directly.
So you mentioned one of the, I guess, the main design ideas was to have the optimizer only care about the graph. And so it seems like lots of the optimizations will be like running more instances of the vertices that do the same thing based on the data that you're seeing. Have you given any thought to maybe if you had some traits associated with the vertices, then you could make some like larger scale optimizations, like the one that you presented with the T?
Right. I mean, as I was saying, it's really the scheduler that knows about the graph, and the optimizations all happen above the fold. So, like in these stage managers. So, certainly you can, both at the beginning when you're constructing the initial static plan, the application level thing, Dryad link or whatever, may know something about the semantics of each of those operations, and it may be able to do whatever optimizations you go up and read up from the literature. If you want to be able to do dynamic modifications that are dependent on the semantics, the way that you do that is by implementing a custom stage manager and putting all the vertices in that stage into that stage manager. So again, it's sort of above the fold, but we just supply callbacks, and then you can do whatever you want there.
Please comment on mechanisms to deal with unpredictable execution times of nodes in the graph.
As I said, the stage manager can collect statistics on, if you have a whole bunch of things which are notionally the same, the stage manager sees the input size, the machine, and the running time of everything that runs. And so you can do more or less conservative things to decide when you think some vertex is running slowly with respect to its peers. And I mean, that's where, of course, you always have a trade-off between if your job is the only job running on the cluster and you had infinite network, then obviously you would always run as many copies as you could of everything until the whole job finished, because there'd be no downside to doing that. And when you have multiple things on the cluster and when they might be coming up the network, then there's some policy you have to decide on between the latency for this guy running more copies of things that might be slow and the throughput of everybody else. And that's really a policy decision.
Did you consider duplicating work more than twice?
Sure.
What were the results?
I don't have an analysis of that at this point. We're hopefully going to have a paper on analyzing a whole lot of this kind of stuff, but I can't really tell you any more at the moment. I mean, we do that, but I haven't got a measurement that tells.
Did you have any upper limit in mind, either for the number of vertices or for the fan in or fan out of any one vertex?
Well, with the current design, the job manager holds the whole graph in memory, so that limits to millions of vertices. If we started running into that, then it would be easy enough to get it to page stuff in and out. So, I mean, there is some overhead to having a vertex run, and so, ideally everybody would write code such that their vertex took sort of 1 to 10 minutes, I think. And then going over millions of vertices would require either a very, very large cluster or a very, very long job, and we haven't really been working in that space yet. But in terms of the fan-in, no, I mean, when we started, we were restricted on the number of things that we could have as a fan-in because we were using SMB to read the files, and SMB doesn't work very well if you have a lot of files open at once. But in more general terms, no, I don't really have much intelligent to say about what the maximum should be. Obviously, having a large fan-out is generally easier.
So I think we're actually running short on time because we've got another speaker coming in right now. But thank you very much for this talk. It was very interesting.